Today we're going to talk about the equivalence in between bond graphs and block diagrams. And we need to establish the fundamental principles upon which block diagrams are built, and also the fundamental principles of bond graphs. In order to illustrate that, I am going to propose an example, a simple example of a capacitor. So I am going to look in here of a capacitor, and I would say to you, this is also like a spring in a mechanical system. But let's say that we have a voltage here, and then we put the current that circulates over here like this, I. So we're going to concentrate on just one element and do first the representation of the block diagrams. I am going to put it on the left hand side in here. And then in here I'm going to say bond graphs. Yeah. Okay, so in this case, isn't it true that I can say that the voltage across the capacitor is equal to 1 over C times the integral of I dt? Let's establish that principle. Right? Yeah. This comes from our basic concept of what a capacitor does. Basically, if the input is the current, you would expect that the voltage on the capacitor is the integral of that current multiplied by 1 over C. So I could very safely say that in my left hand side I have the output, and then on my right hand side I have the input. Yeah? Okay. So if we represent this in a block diagram, we have to represent the input and the output. However, I am going to use deliberately some new words. I'm going to call this the action, and this I'm going to call it the reaction. I also could use the word cause and the word effect. So in other words, a consequence of circulating a current through a capacitor would be to generate a voltage, which is what I'm saying. How do we represent this equation in the way we have learned in block diagrams? What we have in here is that you have an input like this, which is the current I. Then you multiply it by 1 over C. And then you do an integration here. Using the Simulink notation, we integrate. And out of this comes voltage V sub C. Yeah? So see, look here, this is the input. Process the input by dividing it by 1 over C and integrating, and you are going to get this output. Okay? This is the representation of the block diagram. Now, you see the representation of this equation is directly this block diagram. Or you could say the other way, the block diagram is a direct representation of this equation. Doesn't matter which way you express this, the thinking is the same. However, I could write the equations a little different. And how about if instead of writing it this way, let's say I differentiate both sides. And I have that dv sub c dt is equal to 1 over c times I, right? So I could perhaps writing a little different way that my output I is equal to C times d b sub c dt. Okay. Let me just switch colors because I want to compare with the other one, and I'll just rewrite it in red here because I want to make sure that you could actually distinguish. But I'm just going to write the same thing, that I is equal to C times dv sub c dt, like that. See? One conclusion already. This is obviously an integral form. Yeah? And this is a derivative form. Okay. Remember this word, cause and effect. If the cause is this current, it has this integral form. If the cause is this voltage, you have this derivative form. So, we have a representation in block diagram form of this integral form. Let's examine the representation of this so-called derivative form. So if you do that, you see the input here comes, the input is b sub c, and then this input gets differentiated. The input here multiply by c first, because this in here you are going to differentiate, and then you multiply this by c, and out of this comes I. See? So this is the input here, and this is the output. This is the cause and effect. So the representation of the integral form of the capacitor is like this. The representation of the derivative form of the capacitor is like this. Okay, so this is how we represent the equations of the. So you could say, the conclusion that I'm going to perhaps put it in the red color here, it says, you could say the block diagram is, okay, block diagram represents the, you could say the equations of a C element. You could say in either integral or derivative causal form. So when we talk about this concept of causal form, we introduce this word, the word causality. The word causality means which way are the equations written. Okay, so far so good. This is our representation of the C element, and we can use this to build the block diagrams. I told you that the equations come from the block diagrams come from the equations. This very same concept could be used now using a different notation. And in this notation, we create an interesting symbol here. We're going to say this is the C element in here. I'm going to go C element, and I'm going to put a horizontal line in here. Depending on which variable is the output, we will have the output in this particular case. In the first output on this integral form was the voltage, V of C is the output, and the input is I. So if you have this symbol like this, yeah, see, this symbol represents this equation because this is the output and this is the input over here. This form represents this equation. So in this is also the integral form, because here what we are saying is that the voltage V sub C is equal to 1 over C times the integral of I dt. We also are saying that dq dt is equal to I. See, this symbol here represents this. So you could perfectly say, and it's safe to say, that this is equivalent, see? But in Simulink you use this notation. And in here, this notation that we use in here is understood by CAMG. So you draw this in Simulink, you draw this in CAMG, but both mean the same thing. In other words, this symbol here is created in such a way. I want you to be able to see this a little better. Let me make this proposal to you. How about if with your hand you hold this line? See, there is your hand. Yeah? And push it this way with your left hand. Yeah? You feel it hard, you hold it, push it. See, it's like a little piston. And this is what you push it with. So this, we are going to call it the output variable, or in this notation is called the effort variable. And this input, this is called the flow variable. Yeah? So it's just another way of representing the same thing. But if you have it in the other way, let's say this C element in here like this, and then you draw it like the line over here, but instead of the output being the the voltage. Now voltage becomes the input and this becomes the output. So this is input and this is the output. So what are we saying here with this forming here? We can say this is the integral form. And that integral form has these equations. But this is the derivative form. What am I saying with this? We are saying here that the current I, let me just go change the color here, that the current I is equal to C times dV sub C dt. But since dQ dt is equal to I, it follows that dQ dt is equal to C times dV dt. And this equation is the one that represents the derivative form. So we're going to put them like this. And this one in here is totally equivalent to this. Okay? So you have two ways of representing the system. Either like this in block diagram or like this in bond graph notation. With this is a symbol C for the capacitor, this is the output V, and this is the input in this case. Like I said, understand this as if you hold it like from the line and push the piston to the right, you can see that C is putting an output, this V sub C. But now I invite you to hold this over here with your little hand in there and push it to the left. You're going to push it like that. The input is the voltage to the element. See, this is the element, and this is the output. So this notation is equivalent to this, and this notation is equivalent to that. But both of them have the representation of the same differential equations. Okay? So this is how you represent it, and they are equivalent.